Hello, welcome to section 6.5. We're going to talk about inverse trigonometric functions today. Before we even begin into the idea of inverse trigonometric functions, we want to recall a couple of items from our previous chapters. And the first one was, what is an inverse function in the first place? Well, if we recall, if we're given some function y equals f of x, we may have a function's inverse in that we can take the inverse of that function and reverse all of the x and y values from one to the other. Right? So an inverse function is the kind of function that reverses the roles of x and y in our ordered pairs. And we had introduced it using ordered pairs, but we stated that if we had a function y equals f of x, that we can find an inverse such that when we take the inverse function of some value, it undoes the original function. Another way of thinking about this is that inverse functions are the kind of functions that when we take the composition of the function along with its inverse of some value x, it is the same. Get rid of that stray mark up there. It is the same as if we take the composition of the inverse function with the original function of x, and in both cases the result is just to undo whatever was done to x. So what is the requirement for one of these functions to have an inverse? I'll take a moment and think about this, but if you recall, the idea was that it must be a one-to-one function. In order for a function to have an inverse, it must be one-to-one. We tested whether or not functions were one-to-one often if we had the graph by using the horizontal line test. And the horizontal line test went like this. In the horizontal line test, we said that if we were to pass a horizontal line through the graph of our function and look to see if there was more than one place at which that line crossed the graph, then we would say that it was not one-to-one. So the functions y equals cosine of x here in orange and the function y equals sine of x here in purple are not one-to-one. Given the constraints that we have, it would not pass the horizontal line test because these graphs do pass through the function in more than one place. If we concentrate on the sine function, we can see a horizontal line pass through the graph at any point passes through in multiple places. And similarly for the cosine function. How about tangent? Well, we got the same problem. Again, since it's a periodic function that repeats over and over again, we can see that there's many places on this function where the y value is the same. So in this case, these are not one-to-one. None of these are. So I guess the real question for us is going to be, well, if we have the fact that these functions cannot have inverses because they're one-to-one, where the heck do we get off telling everybody that there's such a thing as an inverse trigonometric function? Interesting question. And the answer to that question is, how can we come up with a one-to-one function if we don't know that much about it, is to limit the domain. Now we notice that this is the function from negative 2 pi to positive 2 pi of y equals sine of x. And over this interval, the sine function is not one-to-one. But we want to limit the domain in such a way that we pick values of x, some interval on x, for which the function includes every value that's still in the range. So we want to still go from positive 1 to negative 1 along our y-axis and include all of those values, and still not have any part of the graph not able to pass the horizontal line test. So how could we do that? Well, one way is to limit the domain, and what we're going to do is we're going to limit the domain to be from negative 2 pi, from negative pi over 2 to positive 2 pi. So we would say negative pi over 2 as an interval to positive pi over 2. And let me illustrate that graph by adjusting this picture right here so that we're only looking at that much of the graph. Now in this picture, the domain has been shifted so that the only values of x that we now see start at negative pi over 2 along the x-axis and go all the way up to positive pi over 2. And you'll notice that the y values stay between negative 1 and positive 1, which is what we want, and the x values are limited in such a way that the function is still only 1 to 1. It would pass the horizontal line test. So this is our what we call our principal domain for the sine function. So given that, let's take a look at our principal domain for the cosine function. Where should it be? Well, in this case, limiting from negative pi over 2 to positive pi over 2 isn't really going to help, because that's still not going to make it 1 to 1 and not include every value within the range. So in order to limit that, we're going to change, and we're going to limit our domain from 0 to pi only. Pi being right here, you can see that that's going to happen. So let me adjust my graph so that you can see that. So as you can see, the reset here tells us that we see from 0 to pi, sort of the similar idea that we had before. We're going from 0 all the way out to pi along the x-axis. We retain all of the y values from negative 1 to positive 1 along the y-axis. That's our lowest and highest value, pi over 2 being right in the middle. And we can see what that means right here. Our principal domain makes this a 1-to-1 function. Okay, really quickly, one more function. How do we limit this one? Here it is from negative pi to positive pi, right? And we want to limit that domain. Well, how should we do it? And the answer in this case is that we look at the location of those asymptotes right here, and we note that they go from negative pi over 2 to positive pi over 2. So that's what we're going to limit our domain to as well. And we note that the asymptotes go from negative pi over 2 to positive pi over 2, so that's how we're going to limit. Only slightly different from the graph for sine, we're going to limit this interval and say that x is between, let me get that pen going right here, x is between negative pi over 2 and positive pi over 2, but we're not going to include the endpoints. Notice how that's different than sine. Right? If we go back a slide, we can see exactly how sine includes those endpoints, because we want to include the values at each end of our cycle right here, one period, or half of that period anyways. Right here, we don't want to include those because those are asymptotes. Those would make the function undefined.